Alright guys, this is for October the 26th through the 29th. I will tell you that we are kind of going a little bit of a different direction. We were going to do transformations, but you do not have the material at home to do the transformations. So we're going to kind of skip over that for a while, and then we will come back to that when you guys get back into school in person. Right now we're just going to kind of go into, we're going to skip that whole entire section, and we're going to go into how to prove triangles congruent. Alright, so let's look at this lesson. This lesson is called Congruence Criteria for Triangles, SAS. So you're going to learn why two triangles that satisfy the SAS congruence criteria must be congruent. Alright, so let's look at the first question. The first question is something that you would have done with a partner. It says, answer the following question, then discuss your answer with your partner. Do you think it's possible to know that there is a rigid motion? Now, we should know what a rigid motion is because we did get into that. Remember, a rigid motion is something, a rotation, reflection, translation, that preserves or keeps the angle measure and the segment lengths. So do you think it's possible to know that there is a rigid motion that takes one triangle to another without actually showing the particular rigid motion? Why or why not? So in other words, what it's wanting to know is, do you think that that it's possible that I would know that there is a rigid motion going on without actually showing you every single step that is happening? So this is kind of an opinion question. So you may think that it is not possible because it's necessary to show the transformation as proof. Some of you may believe that you can do this by looking at our triangles carefully. Alright, so that's what we're going to be looking at now. We're going to be looking at, can we do this? Alright, so we're going to see this SAS. This next part is a lot of discussion. So we're just going to kind of look at it and talk about it so that you kind of understand this a little bit better. Alright, so let's look at the discussion. It said, it is true that we will not need to show the rigid motion to be able to know that there is one. So right there it tells us we don't have to show every single transformation happening in order for us to know that there is a transformation. We are going to show that there are criteria that refer to a few parts of the two triangles and a correspondence between them that guarantee congruency. For example, the existence of rigid motion. We start with the side angle side, or the SAS criteria. You will find this in your notebook, which, by the way, if you have not turned in your notebook, you need to get that turned in to me within the next week, because if not, then it will be a 0 out of 150. So we start with the side angle side, or the SAS criteria. So this right here explains it to us. It says the side angle side triangle congruence criteria. If you are given two triangles, triangle ABC, and then triangle A prime, B prime, C prime, this right here, this A prime, B prime, C prime, is the triangle that has been transformed in some way. This is going to be our pre-image. This will be our image after the transformation. So that A prime is equal to, AB is equal to A prime, B prime. That's our side. Measure of angle A is equal to the measure of angle A prime, which is our angle. And AC is equal to A prime, C prime, which is our side. Then the triangles are congruent. So if I have side angle side, then I can prove our triangles are congruent. The steps below show the most general case for determining a congruence between two triangles that satisfy the SAS criteria. Note that not all steps are needed to every pair of triangles. For example, sometimes the triangles will already share a vertex. Sometimes a reflection will be needed. Sometimes not. It is important to understand that we can always use the steps below, some or all of them, to determine a congruence between the two triangles that satisfy the SAS criteria. Alright, so let's look at this. It says proof. Provided the two distinct triangles below, you're going to assume that AB is equal to A prime B prime, which is our side, that the measure of angle A is congruent to A prime, which is our angle, and that AC is congruent to A prime C prime, which is our other side. Notice the markings. This side's congruent to this side's congruent to this side, and our angle is congruent to our other angle. Alright, those markings are very important. By our definition of congruence, we will have to find a composition of rigid motions that will map A prime, B prime, C prime to A, B, C. So we want to know, how would we map our transformed figure back to our original figure? We must find a congruence F so that F of A prime, B prime, C prime is equal to triangle ABC. First, use a translation T to map a common vertex. Which 2 points determine the appropriate vector? Alright, well, let's look at this vector. The appropriate vector would be A prime and A. Alright, these are our angles that are congruent. So what 2 points determine? That would be A prime and A. Can any other pair of points be used? Why or why not? No, because those are the only angles that are congruent by assumption. Okay, so that is the only 2 points that I can use, because those are the only 2 points of angles that are congruent. Alright, so that's why we're looking at that vector. State the vector in the picture below that can be used to translate A prime, B prime, C prime. Okay, so really quickly, let's kind of talk about what it means to be a vector. I was going to give you the technical definition of a vector. So if you'll give me 1 second. And it wants to give me everything else other than... so a vector, the best way that I can explain a vector is something that we can add. Alright? So trying to figure out something we can add to our figure in order to create our translation. Alright? So it wants to know, what can I add to my picture that can be used to translate this figure to this figure. So I can actually create a ray. And if you'll look at this next picture shows you that ray that we can create. So I can create ray A prime A. In other words, that is where I can kind of either slide my figure along or rotate my figure along. That is what a vector is looking at. Using a dotted line, draw an immediate position of A prime, B prime, C prime as it moves along the vector. All right, so it wants to know what's going to happen. So as we move along this vector, my triangle is going to move this way. Okay? Now, we didn't use a dotted line. They drew a solid line for us. But this point is going to move along this line, this vector here, till it gets to A. So think about what that's going to look like. After the translation, or that slide, then we show that it shares one vertex with triangle ABC, which is A. In fact, we can say this. We can now say that the translation, all right, that T stands for translation, the translation of, and I need to put this A prime A here, tells me what I'm translating. So the translation of A prime A of triangle A prime B prime C prime, because that's the triangle I did, equals A, and I am going to equal that to A because I'm back to the original point. But then I have translated B again and C again, so now it becomes a double prime. Because that tells me that now I have a second translation. Alright? So A is going to, so A prime goes back to A because it now is the same point. But B and C still are not the same point. So therefore, this is now a second translation. Alright, so next, we use a clockwise rotation. So now I'm going to write this like this. I'm going to rotate angle CAC double prime. Alright, so I'm doing CAC. I'm going to rotate this angle right here clockwise to bring the side A double prime to AC. Alright, so I'm rotating. So I've done a slide so that my A goes back to my point, my A prime goes back to my point. I've gotten it to this point. Now I want to do a rotation, a turn, so that my sides meet up. So I'm doing a clockwise rotation. Okay? And I know this is kind of difficult to understand since we are skipping the the transformations section, but I just don't feel comfortable enough trying to teach that to you virtually. You have to have a lot of hands-on stuff. Using a dotted line, draw an intermediate position of triangle A prime, B prime, C prime as it moves along the vector. or I'm sorry, I'm rereading a section that we've already done. Alright, so I've got to turn my page. A rotation of appropriate measure will map segment AC double prime to segment AC. But how can we be sure that vertex C prime maps to C? Alright, so look. I now have this segment mapping to this segment. But it says, how can I be sure that vertex C maps, or vertex C double prime maps to C? It says, recall that part of our assumption is that the lengths of the sides in question are equal. That's what those marks stand for. So if those sides are equal, then it tells us that the rotation of C double prime will be fine when we map it to C. So now I know that AC is equal to AC double prime. The translation performed is a rigid motion and thereby did not alter the length when AC double prime, or I'm sorry, AC prime became AC double prime. Alright, so now we have done our rotation. Here's what our figure looks like. After the rotation of angle CAC double prime to B double prime C double prime, a total of two vertices are shared with triangle ABC, A and C. Therefore, here's what we can say. We can say the rotation of angle CAC double prime of triangle AB double prime C double prime is going to be equal to the triangle AB double prime C. Because we've now put A and C back together, the only point that we have not done is B. Alright? So B is still double prime because we haven't mapped it back to the original figure. Alright, hopefully you guys are with me. I know it's hard to understand. Finally, if B triple prime and B are on opposite sides of the line that join AC, a reflection, and we would write it like this, right here, reflection of AC brings B triple prime to the same side as B. Alright? So since a reflection is a rigid motion and it preserves the angle measures, we know that the measure of angle B triple prime AC is equal to the measure of BAC. And so, AB triple prime maps to AB. If, however, AB triple prime coincides with AB, can we be certain that B triple prime actually maps to B? We can, because not only are we certain that the rays coincide, but also by our assumption that AB is equal to AB triple prime. Alright? Like I said, I know it's a lot of terminology, a lot of stuff, but guys, it's really not as hard as it sounds. Another way to visually confirm this is to draw the marks of the blank construction for segment AC. Alright, so we could draw a perpendicular bisector. Alright, we can actually do a perpendicular bisector construction for AC. Write the transformations used to correctly notate the congruence, the composition of transformations that take this figure back to our original figure. Alright, so here's what it wants to know. What did we do? How did we do this? The first thing we did was we did a translation. Alright, if you go back, the first thing we did was we did a translation, which is a slide. We slid our figure over. Alright, the second thing we did a rotation. Okay, if you remember here, we rotated this angle, and so they were matching. Then we did, for our last, we did a reflection. Okay, we did a reflection. So here's how I would write this. And do not look at this and go, oh my gosh. Alright, so here's how we would write this. H is our end. Alright, so we're going to do H of G, of F, of triangle A prime, B prime, C prime, is equal to triangle ABC. So in other words, it's telling me that I'm going to translate my image, then I'm going to rotate that image, then I'm going to reflect that image, and it will give me back my original formula, or give me back my original figure. We have now shown a sequence of rigid motions that takes triangle A prime, B prime, C prime to triangle ABC with the use of just 3 criteria from each triangle: 2 sides and an included angle. Given any 2 distinct triangles, we could perform a similar proof. There is another situation when the triangles are not distinct, where a modified proof will be needed to show that the triangles map onto each other. Examine these below. Note that when using the side angle side triangle congruence criteria as a reason in a proof, you need only state the congruence as SAS. One of the other things that I need to point out, because they have not done this yet, notice that my side angle side is in order. It is 2 sides, and it must be the angle in between those 2 sides. Alright, I'm going to repeat that one more time. When I have 2 sides, my angle must be the angle between those 2 sides, which is why we read it side, angle, side. Okay? Alright. So let's look at this. Example number 1. It says, what if we had the SAS criteria for 2 triangles that were not distinct? Consider the following 2 cases. How would the transformations needed to demonstrate congruence change? Alright, so if I had a shared side, what would I have to do to these 2 triangles to be able to prove that they would be congruent by side, angle, side? Well, they share this side here, so we know it's congruent. They share this angle here. The only thing we've got to do is figure out this side here. Guys, all I would have to do is fold that, and that would be a reflection. What if I had a shared vertex? At this point in time, I would have to rotate this angle. So we would need to do a rotation. Then it would end up looking like this. So then I would just have to do a reflection. Okay? Given triangles with a pair of corresponding sides of equal length and a pair of included angles of equal measure, sketch and label 3 phases of the sequence of rigid motions that would prove the 2 triangles to be congruent. Alright, so here's my original, and mine are not going to be perfect, but that's okay. I don't expect yours to be perfect, so hopefully you're not going to expect mine to be perfect. Alright, so here is my first thing. I want to figure out what I'm going to do here. Remember, when I'm doing this, I can do a vector. In other words, something I can slide across. Alright, so when I do that, this is what I end up with. Once again, I'm not going to be perfect here. So I can actually do a translation. And I am going to bring this point here. So I'm going to draw that vector. And mine should be perfectly straight, but it's not. It's okay. So I'm going to bring this along this vector. I'm going to slide it down. Once I do that, then I'm going to end up with a figure that looks like this. Alright? I'm going to end up with a figure that looks like this. Alright? So when I end up with a figure that looks like this, what am I going to need to do? I'm going to need to do a rotation. Alright, so let's draw our rotation. And we're going to need to talk about which way we need to rotate. Alright, I need to make sure I continue with my markings. So I want to rotate it. I need to rotate it this way. So I'm going to rotate it clockwise. Alright. When I do that, my figures end up being side by side, so they're going to look like this. Now what do I need to do? I need to do a reflection. I need to do a reflection right through here, which will take my figures back to the original. Alright. Justify whether the triangles meet the side angle side congruence criteria. Explicitly state which pair of angle or side or angles are congruent and why. If the triangles do not meet the SAS congruence criteria, describe the rigid motions that would map one triangle onto the other. I'm sorry, if they do meet the SAS criteria. Alright? So I'm given that angle LMN is equal to the measure of angle LNO, and I am given that MN is equal to OM, which I'm thinking that they've given you some wrong letters there. That should actually be LNM, because according to the markings, and this should be ON. Okay? So you need to change that. They have a typo there, according to our markings. Okay. Do triangle LMN and triangle LOM meet the SAS criteria? Alright, well let's look at this. We're going to kind of walk out a proof here. We're just going to write down what I know. Alright, well I am given that angle LNM is equal to angle LNO. Okay, so there is an angle. Alright? And I'm going to put an angle there, just so I can kind of keep up with it. Alright? I am given that MN is equal to ON. That is given. That is a side. So the only thing else that I need to prove is I need to prove a side. Now remember, it needs to be side, angle, side. So I need to prove that LN is equal to LN. Can I prove that? Yes, I can, because of what we call the reflexive property. They are the same exact side, so therefore, I can prove that they are equal. So LN is congruent to LN. So can I prove that triangle LMN is equal to triangle LOM? I have side, angle, side, so yes I can prove it to be side, angle, side. How would I translate, how would I show this with my basic rigid motions? All you would have to do would be do a reflection, okay? Because they share a side, all I'd have to do is reflect across that side. Alright, let's look at this. Given that the measure of angle HGI, this angle here, is equal to the measure of angle JIG, this angle here, and then HG is equal to JI. So I've got a side and I've got an angle. Alright, so HG is equal to JI. That is given. Angle HGI is equal to angle JIG. That is given. There's my side. Here's my angle. That means I need to just see if I can prove another side congruent. It's got to be a certain side. So if I have side, angle, this has to be the side that I have to prove congruent. Because it's the same side of both triangles, once again I can prove that GI is equal to GI. It's equal to itself because it's the same by reflexive property, which would be my other side. So can I prove that triangle HGI is equal to triangle JIG? I can by side, angle, side. And how would I map this onto the other? It would not be a reflection, because if I reflected this, they would not match up. So I have to look at this. More than likely, it's going to be a rotation. I would do a 180-degree rotation. All right. Is it true that we could also have proved triangle HGI and triangle JIG meet the SAS criteria if we had been given that angle HGI is equal to angle JIG and HG is equal to JI? Explain why or why not. If we had been given that the measure of angle HGI and JIG were equal, and that HG and JI were equal, well, that's the same information they just gave us. So I'm not really sure why that question is different. Unless I'm missing something somewhere. Congruent. That's what I'm missing. Look at my signs. It's not that they are equal, it's that they are congruent. If I know they're congruent, what do I know? Whenever angles are congruent, they are also equal. Okay? Writing the same thing. They are considered equal. So yes, I still could have proven this to be true. Alright guys, like I said, I know this is not the ideal situation, but do your best with what you can on the work. If you are a B-Day student, unfortunately, you do have the rest of the week that we had not finished. Guys, I'm not expecting you to try to get it all done before the end of next week, but you need to get it done and turned in to me as soon as you possibly can. If you need anything, reach out to me through email. I'm not sure what days I'll be available next week because I'm not sure what's going to be happening here. But just let me know if you need anything.